Okay, so hello Insomnihack and welcome to my talk about VirtualBox security. Just a quick reminder what VirtualBox actually is. It's a product developed or maintained by Oracle that essentially lets you run all kinds of modern operating systems inside virtual machines, very comparable to, say, VMware Workstation. But it's open source and free, so that's nice. Just a quick intro of myself. I'm an independent security researcher, sometimes studying. I'm interested in reverse engineering and exploitation. I did Pwn to Own last year, and then I was very happy to hear that they added VirtualBox as a target this year. So that motivated me to look at it again and come up with a new exploit. But unfortunately, I can't present that today because the bugs are not fixed yet. Instead, I will be talking about some research I did last year. All of the bugs are already fixed. I love playing CTF. I play usually with the team Eat Sleep Pwn Repeat. And together with some friends, I started the blog last year about, let's say, 0 days and browser exploitation, which you can find at phoenix.re. If you want to contact me, Twitter is probably the best option. And I should also point out that some of this research presented was sponsored by the security team Secure Disclosure Program, run by Beyond Security, which can be found at this link. All right, so why do we even want to look at hypervisors, or VirtualBox in particular, in terms of security? Well, we all know that VMs are very useful for developing software, testing software, debugging, especially kernel debugging. But it's also useful as like a certain means of isolating dangerous code, let's say. So for example, if you want to analyze the behavior of some malware, you probably don't want to run it on your host to find out what it does. And instead, you might decide to run it in VM, assuming that it's kind of safe to do so because it's an entirely different operating system and can't really affect your host system. But there is definitely some attack surface that could allow for dangerous code running inside a VM to break out of it. And we know that some competing products like Hyper-V and VMware, they've had quite some bugs in the past that were published. Both of them, no, well, one of them has a bug bounty program. The other one has been a target at multiple exploit competitions so far. So we know that there's been quite some research, quite some interesting exploits that allow guest code to escape to the host. But both of them are closed source and they're kind of hard to reverse engineer, and people tend to use fuzzing because there are not a lot of symbols available. And in comparison, VirtualBox is really good because it's open source and you can read everything. You can really understand in depth how features are implemented, how device drivers, emulated devices are implemented. So it's really nice to learn about hypervisors using that code base. And also for exploitation, they're quite nice, especially VMware and VirtualBox, because they're quite far behind, say, modern web browsers when it comes to exploit mitigations. So you will definitely not find something like CFI or sandboxing in, well, maybe in Hyper-V, but not in the other two. So it's kind of a state from 3 years ago. So if you find issues, they are often exploitable, and you can really make impactful demonstrations. Also, it's fun to play with hypervisors if you want to learn about low-level I/O and programming and kernel programming, because more often than not, you will have to write parts of your exploits or parts of your proof of concepts as kernel drivers, because you need access to low-level hardware, emulated hardware in this case. Yeah. So if you're interested in low-level stuff, it's a cool way to get into it. All right, so I will start out my talk by giving a short overview over the architecture of VirtualBox, and then introduce you to the, let's say, the three most important privilege boundaries that there are within VirtualBox, one of which is kind of unique to VirtualBox and not that well known. And then I will give you examples of bugs that can occur in each of these boundaries that allow you to cross them. So this is a very high-level overview over the architecture. I put the host and the guest here side by side, although obviously in the real world the guest is inside the host, but it's hard to visualize. So let's just assume the server-client type architecture here. And then both in the host and the guest we have the typical separation between user and kernel land. And I think the most important part is the, wait, what did I do? Whatever. What? Wait, so maybe I can't use this? Maybe somewhere here. So let's say this here is a host process called virtualBox.exe, which is in the user land of the host, and you will have one of these for each VM that you run. So every running VM will have one of these processes, and they will make use of a kernel component called a VBox driver. What the hell? And use an interface provided by that driver to implement the low-level functionality. So we definitely have a privilege boundary here, and it will be interesting to see if we can cross that to do privilege escalation on the host. And on the guest side, we also have user and kernel land, and if we install guest additions, then there will be an additional kernel component called VBox guest, which is a kernel driver running in the guest. And maybe that exposes some functionality that we can use to escalate privileges inside the guest. And then, of course, we have the most interesting boundary, which is between the host and the guest. If we cross that, then we get a VM breakout. And most of the interfaces there are just your standard low-level I/O, like memory mapped I/O, port read-writes. The devices are typically exposed via PCI, and they speak protocols like VGA or USB. But we also have at least two VirtualBox-specific protocols here called HGCM, Host Guest Communication Manager, and HGSMI, Host Guest Shared Memory Interface. And these implement VirtualBox-specific functionality. Okay, so first we're going to focus only on the left side of this diagram. So we're just going to ignore the guest for a second. And we want to know, can we cross this boundary from the user land in the host to the kernel land, thereby obtaining a privilege escalation inside the host? So can we, as an unprivileged user on a machine where VirtualBox is installed, can we make use of this VBox driver to escalate privileges? And yeah, for that I have to explain a bit what this driver actually does. So it implements all of the functionality that needs to be implemented in the kernel, such as the virtualization, VM enters, VM exits, low-level memory management, low-level I/O, essentially everything that cannot be handled in user land. But this interface is pretty weak. So it has had a couple of issues in the past. So you will have, in that kernel driver, you will have your classic memory corruption issues. I know this is probably hard to show because of... All right, so, oh God. All right, so this is a bug report by Jan Horn. No, it doesn't work anymore, okay. This is a bug report by Jan Horn from Project Zero. I'm just going to read out the important parts now because I can't mark them. It says, this I/O control called VMMR0, it takes a kernel pointer as an argument, and then it uses that pointer to load and store various kernel registers, including RSP, which is the stack pointer, from this essentially attacker-controlled location. So of course, if we can control the RSP register in the kernel, we can probably turn that into code execution somehow, and then we have code execution in the kernel. So if we can do that from an unprivileged context, then that's a privilege escalation. But Oracle says this is not a bug, because you should not be able to get a handle to this VBox driver in the first place. So their threat model is they want to protect this driver itself. So you're not supposed to get a handle to this driver. Otherwise, you can do all these kinds of things, and they know about them, so they don't even try. There's another issue, which is there are some data structures that are mapped in both user and kernel land, and they have kernel pointers inside of them. For example, here we have two versions of this VRAM pointer. One is suffixed with R3 for ring 3. One is suffixed with R0. And the R0 version is used by the kernel, but it's writable by the user land because it's also mapped there. This is, by the way, a data structure that captures the state of the VGA device. And there's plenty of examples of this. And if you change this ring 0 pointer from user land, the kernel might do interesting things with it. And there is even much more direct ways to get code execution using this driver. So really the bottom line here is you don't want anybody to be able to access this driver in the first place. Okay, but how can this work? Because if you start a VM as an unprivileged user, well, if VirtualBox is installed, everybody can start a VM and create a VM. And if you start a VM as an unprivileged user, it will actually run as an unprivileged user. So the host process will run as the user that started it. So how can this even work? How can they then make this driver not accessible by an unprivileged user? And the way they do it on Linux is, if you look here at the second output, you see the permissions for the VBox driver device. It's owned by root, and it can't be accessed by anybody else. So only root can open a handle to this file. And then the VirtualBox process itself, it is also owned by root, and it has the setUID flag set. So the first thing it will do when it starts is it will open a handle to VBox driver, and then it will drop privileges back to the user that started the VM. And after that, it's just an unprivileged process, and it can't open the device anymore. But of course, it has somewhere in its global memory, it has this file descriptor stored. So in the last line, you can see a running process, and you can see that it's actually running as an unprivileged user, but it has this handle open. And the good thing about using a setUID for this is that on macOS and Linux, this will actually prevent the simple means of getting code execution, injecting code inside this process, just for security reasons. So you can't use ptrace or the equivalent debugging API on macOS to inject code into it. Because if you could do that, then you could get this handle out. On Windows, this protection mechanism is much more complicated because they have to implement it completely by themselves because there is no equivalent to setUID. So what they do is, if every time somebody tries to open a handle to this driver, the driver itself will check, well, what's the process name of the process that wants to open a handle? Is it signed by Oracle? Is it called virtualbox.exe? Is it in a trusted location? And only then will it allow the handle to be opened. And it will also install a lot of hooks that prevent like your standard code injection techniques, like create remote thread and similar. And they also hook the DLL loader so that it will never even try to load any unsigned DLLs. And there is a very good overview by James Forshaw from Project Zero about the implementation of this. Okay, so if we somehow bypass this protection mechanism, then and then get code execution in this protected process, we can get a handle to VBox driver, and if we have that, then we will see that we can achieve a privilege escalation. So how has it been done in the past? Well, there's your old school like environment poisoning, where in 2017 Jan Horn reported 2 similar issues on Linux. One was based on an environment variable that Qt uses to load additional plugins. So if you set that, you can make it load shared libraries into the process. You can get the handle out. There is a similar issue with the Elsa config file. It can also be made to load additional shared libraries. And James Forshaw found like several bypasses for the implementation on Windows, which is even more complicated. And all of these are described in the blog post as well. Now, some other ideas that I had of additional attack surface that you might look at if you're interested in this kind of exploit is, well, there is a lot of files that VirtualBox stores on disk and then parses again later. Some of them are binary formats, and I'm pretty sure if you mess with some of them, you can probably like get memory corruptions inside the parsing process, which is the protected process. And there is also a programming interface based on COM, which allows you to make method calls and interact with the VM. And I will show you an example of a bug there in a while. And then every VM escape is also automatically a privilege escalation. That sounds weird because VM escapes sound much more powerful than that. But maybe you have a VM escape that only works in like a very obscure configuration. But then what you can do is you can create a VM with that configuration exploit it, and then essentially from the inside you can exploit this protected process again and achieve a privilege escalation. One example of such an obscure configuration, which is actually not that obscure, is if you enable 3D acceleration in your VMs. And the documentation says, well, you should never do that if you don't trust the guest, because amongst other things, enabling 3D acceleration enables a lot of additional program code in the virtualBox host process. And it even says which it might be able to use to crash the machine, the virtual machine in this case. And that's very true, actually. Just this year, somebody just reported a bunch of bugs in that component, and they're just trivial integer overflows that lead to heap buffer overflows. Some of them are even stack-based buffer overflows. Probably at least some of them are pretty easy to exploit. So if you exploit one of these bugs, you also get a privilege escalation. And there's definitely more. So I've reported some more, and I know of at least one other person that reported some more of those. This code is from 2001, so it shouldn't be that surprising that there is lots of issues with it, because nobody's really looked at it since. And only now in 2017 and 2018 people start to look at it. Okay, this is probably very hard to see from the back. This is a bug I reported in one of the COM methods. It's called set credentials, and you just give it a username and password, and it will store those, and later it can auto log in the guest operating system using those credentials. And it just takes your username and password and string copies them into a fixed size buffer on the heap. So yeah, you would hope to not see that in a modern code base. And also you would expect the compiler to be smart enough to mitigate that, because it knows, in this instance, it knows exactly how large the buffer is. So MSVC, the Microsoft compiler, and GCC, they both add like bounce checking. For some reason, Clang doesn't. So the macOS build was vulnerable, and it was fixed in January. So I decided to write an exploit for that, to demonstrate a full privilege escalation chain using that. One problem here is that this buffer is at a constant location, because it's allocated exactly once at startup, and you can't reallocate it later. So we have to get a bit lucky and be able to override something afterwards that's interesting. But turns out in about 30% of the cases, if you just send this username, which is a bit too long, you will get this crash. So you can see here it crashes at the address 0x42424242. This is actually not, this is a memory access where it crashes. It's not RIP control yet, but it crashes while accessing this address, and that's just the last 6 characters of the username that we passed. And what this actually does is we override a pointer to an object, then it uses that object to fetch a function pointer, and then it calls that function pointer with the object as the first argument. So that's quite a powerful primitive. So if we can somehow fake an object somewhere and make it fetch a function pointer from there, we get immediate control over the code execution. Yeah, so one thing to point out is that we don't actually have to defeat the normal ASLR of all the libraries, because they're all, in every process on macOS, they're in the same location. So we can just look in our own process where is some function loaded, and then we know where it's in the target process as well. And in order to place a known payload at a known address, I just used an old trick that's also quite well known on macOS. It's just very poor at randomizing mmap allocations. So if we just allocate a lot of memory inside the guest, like 1 GB, then one of these pages will end up at this address. And then we just use a gadget that loads a lot of registers from our object, and we get ROP, and then we get code execution. Here on the right, you can see that my shellcode is executed at somewhere in this fake object. Okay, so now we can now we have this handle to the VBox driver, and I haven't really told you yet what to do next. And definitely the easiest way that I found is just use the API that does that. So there's a library, there's an IO control called loader load, and it's used to add plugin code to the running kernel driver. So if you install, say, the extension pack for USB support, it will just add a plugin to the already running driver, and it does that by using that API and just passing it the driver that it should load as a memory buffer. On macOS it does no additional checking, so you just take any of the existing modules, you change the entry point to contain your shellcode, you give it to this function, and then it will execute it in the kernel. So that's probably a bit too easy. And on Windows it's a bit harder, but also possible. There it will actually check that the driver that you give it has a valid signature. But there is a lot of already existing drivers, and maybe we can use one of those signed drivers and reuse some of its code to our advantage. And for that we need another IO control, which is called call service, and it allows us to call a function inside a kernel plugin. And for that function call we control 4 arguments, I think, and the last one is a 64-bit integer, so we fully control it. So we just need to find a gadget that jumps to that register, and there is plenty of those. R9 is where the 4th argument will end up being stored. So we just specify this jump R9 gadget as the function that we want to call, and we immediately get control over the RIP register for the program counter. We're not completely done yet, because on Windows, at least on modern Windows 10, you can't just jump into user land because of SMEP. So we need to somehow get some interesting code into the kernel. But that's also easy because there is other IO controls that let us allocate executable code in the kernel and write to it. So we place our shellcode there, and then we jump to it. And then we again have kernel code execution. So this is the full exploit for macOS for version 5.2.4. So I'm starting, it's probably also hard to see, I'm starting out as an unprivileged user. Then it creates a VM, it starts the VM, it runs a heap spray inside the VM, and then it triggers the bug, and we end up with a root shell. All right, so let's look at the right side of this now. So ignore the host for a moment. We have this weird additional driver called VBox guest, which is installed if you install guest editions, and we're interested if we can maybe abuse that to do interesting things within the guest. And probably the best thing to do would be to escalate privileges from user land to kernel land inside the guest. So why is this even necessary? So a lot of the features that VirtualBox has require cooperation of the guest. For example, mouse pointer integration, shared folders where you make a subset of your file system accessible to the VM, clipboard sharing, drag and drop, and even this also this notorious 3D acceleration. And most of these are implemented using the HGCM protocol, which is just a very simple remote function call protocol. So the guest can allocate a request buffer with some arguments, and then a service on the host will handle this request and copy the response into the guest. And if you want to use this protocol, you need to make a request to the VBox guest kernel driver, and it will then package it properly, notify the host via some emulated device so that it can get handled, and then it will give the response back to you. So this is what the role of this VBox guest driver is. And there's a weird, there used to be a weird bug in that I don't quite know if it's really fixed yet, but I think at least the examples that I gave them why this is bad are fixed. So if you look at the devices that are exposed by this kernel driver, It's actually two. One is called VBox Guest, and the other one is called VBox User. And VBox Guest is not accessible to the world, only to root and a user named VBox Add. But VBox User is actually accessible to anybody. And by that I mean even to unprivileged processes running inside the guest. And they essentially implemented the exact same interface with almost no distinctions. So everybody can just open this VBox User device and make arbitrary HGCM calls, thereby reading and writing arbitrary files to shared folders, even if they're not mounted, setting clipboard contents, reading clipboard contents, initiating drag and drop, all kinds of things that you wouldn't intuitively think should be possible from that context. And especially the shared folders are problematic. And one example I gave Oracle that where this could be a problem is if the shared folder is actually mounted inside the VM, which it probably is, because otherwise why would you have it in the first place? So let's say it's mounted as root. So what we can do as an unprivileged user, we can just create a shell via an HGCM call in that shared folder. I mean, it will then appear in this mount point because it's mounted. So we essentially just bypass all of the Linux file system permissions inside the guest. And then we can even chmod, or we could, now we can't anymore, but we could just chmod that and set the setuid flag. And then if we run it, we get a root shell. I'm just going to skip over the second one, but the last one I thought was fun. So there is a feature called memory ballooning, where the guest can essentially tell the host, so this physical page of memory I don't need anymore. You might as well use it for, or assign it to some other VM, or use it for yourself. This is essentially just a way to save a VM memory. But this was possible via this VBox User device, so everybody could do it. So everybody could just say, look, I don't really need this physical range that corresponds to the page tables of my system. And then the host would just unmap that and map a 0 page there. And let's just say the operating system is not going to have a very fun time afterwards. So it just crashes immediately. And so you DOSed the guest from inside the guest. So when I told them about this, they essentially just got rid of this VBox User device in the next release. And I thought that was quite a good patch because maybe there's other examples where this could go wrong. But then they noticed that, well, for some reason, some of their features actually use this. So that's probably why it was there in the first place. Somehow they didn't catch that during their testing at all. And then people complained that 3D acceleration doesn't work anymore. And then they just undid the patch. And instead they fixed these individual issues that I gave them as examples of why this could be a bad idea. But you can still read and write files and everything, and I think it's still kind of unintuitive. But it's not technically a security problem. I guess it depends on how you look at it. All right, so this part is now going to be about the real fun stuff, which is escaping a VM and getting code execution on the host. So we're looking at this privilege boundary right here now, and we want to see, is there any, is this interface attackable somehow? Is there code that parses guest provided values that could have bugs, and then maybe you can achieve a memory corruption in the host? So essentially we can think of the hypervisor here as a server and the guest as a client that uses hypervisor functionality and manipulates its state via the emulated devices that are exposed to it. And there are multiple devices that are usually available. So you'll always have the virtual machine monitor device. It's what handles all the HGCM protocol and other VirtualBox specific features. And you will always have a VGA device for graphics. And depending on what guest operating system you use, you will have one of two audio devices attached. And then depending on your network configuration, you will, in most cases, have an emulated E1000 network card. But if you choose to use VirtIO Net, then that is not there. Instead, you have para-virtualized networking. And then you can also choose to use NAT together with your E1000 network card, which means that all the traffic gets tunneled through the host. And there is an extra library that handles all this translation. So that's also a attack surface. And then there are some other things like storage controllers that I think not a lot of people have looked at these. Like USB, I don't know if anybody has ever looked at the implementation. So there's lots of opportunities to get creative and like read some code and maybe find some more bugs in there. So these are the most important examples of full VM escapes that I know of from last year. And as far as I know, it's only last year that people really started looking at virtualBox. So from before that, I don't know a lot. Well, except for 3D acceleration, because everybody's always attacked that because it's so easy. Starting in 2014, and now in 2018 as well. And it will keep on giving, I'm sure. Yeah, and Jan Horn from Google Project Zero, he looked at some components last year. He found like a path traversal bug in the shared folders where two VMs could essentially cooperate by erasing a symlink, and then they were able to together to break out into the host file system and not just the subdirectory that was shared. And he also found a heap buffer overflow in the NAT library, and another heap-based bug in virtio net, which is non-default. And he wrote exploits for all of these. And somebody else looked at the E1000 network card and also found a buffer overflow in there. I think it was inside a bigger structure, so he would then override an offset and then get a heap memory corruption from that. And I think he also at least wrote a pretty good proof of concept. Not sure if he wrote a full exploit, but it's probably exploitable. And then towards the end of last year, I reported two very similar bugs in the VGA device that are essentially just arbitrary memory read-writes in the whole address space of the host. And I want to show you now these last two bugs and how I exploited them. Yeah, so aside from HGCM, you also have another protocol to do host calls, which is HGCMI, for host guest shared memory interface. And the way it works is that there is a shared memory buffer that is both mapped in the host process and in the VM, and it's called the video RAM. And if the guest wants to make an HDCMI request, it will allocate a buffer in that shared area. It will then put its request there, tell the VGA device at what offset the request is, so that it can then go on and parse the request and pass it on to the correct HDSMI service. And there is only, currently I think there's only one HDSMI service, which is the VBVA subsystem short for VirtualBox Video Acceleration. And one of the things that it implements is something called Video DMA. So the guest can tell the host to copy data around inside of the VRAM. I don't know why this is necessary, and actually I think none of the client code actually uses it, so it's just dead code. But it had really good vulnerabilities. So, and it's been there for 6 years. So maybe there used to be some guest code that actually used them, but now it's just good for exploitation. So this is one of the bugs, and the other one is very similar. Yeah, it's probably, let me just put this here. Maybe you can at least see this in the top right. So it just takes a bunch of guest controlled values as offsets into the VRAM. It doesn't do any checking, and then it mem copies data around based on these offsets, and the size is also controlled. So it's a mem copy where you fully control the source and the destination and the size. The only problem is that it's relative to the beginning of the video RAM buffer. But it can be before or after it because it's a 64-bit offset, so it wraps around. So it's a really good primitive. And now by copying data out of the VRAM inside of it, we can leak information. And by copying data from inside the VRAM out of it, we can overwrite stuff that's outside of the VRAM. But we still don't know where this VRAM is actually located in the host. So ASLR is still an issue. And now the question is there anything surrounding this video RAM buffer, or can we place something around it that's interesting, that has interesting pointers, or that would be interesting to corrupt? One way to do this is a heap spray. I haven't actually tried this back then, and I think it would work. Instead, I just looked at what's immediately after the video RAM, and by pure luck, there is something there that's really interesting. But only on Windows. So this is a memory dump of what's directly after the video RAM. So I'm dumping memory here. Well, the video RAM is mapped at C5D0000. Then I'm mapping what's after it. And you can see there's actually a pointer to the video RAM directly after it. And the size is also somewhere in that region. So that looked pretty good already. And then I tried to find out what data structure that is. It's called a memory MMIO range. And it contains all kinds of interesting pointers. It contains a pointer to the VRAM. It contains the size of the VRAM. It contains a pointer to some context data structure for the VGA device. And it even contains a pointer into a DLL. So we already defeated ASLR with this as well. So what we do now is we just read all of these pointers. Then we know where the VRAM is. So now we can do an absolute read and write, because we can, so we can just always subtract the VRAM and then use that as an offset. And we can now read and write memory from everywhere. We already defeated ASLR because we leaked a module base. And now we just need to chase some pointers to find kernel 32. And we find a function pointer that's worth overriding. And there's a really good one that we can trigger via VBVA. And this is code that's normally not called, so we can, if we overrode this pointer, we can then call this and trigger it. And the function pointer here is called PFN VBVA guest capability update. So we just override that with our own code pointer, and we pivot into a ROP chain, and then we get code execution eventually. All right, and then after we get code execution, we run a privilege escalation payload using the trick that I showed you before, and then we get system level code execution, and we can even repair everything so that the VM keeps running. And I will just show you a live demo of this right now. All right. So first of all, I added a kernel driver to this guest that gives me some low-level control over the video RAM and the HDSMI calls. So this exploit requires having root in the first place inside the guest. Yeah, and then we just leak the, well, we can learn the size of the VRAM, then we leak a couple of pointers, then we write some shellcode somewhere, and then just for added tension, it will just wait 20 seconds, and then hopefully afterwards it will give us a shell. All right, so now we have a shell on the host, and this doesn't even need networking. Networking is completely disabled in the VM. It's tunneled through the video RAM. No. And we're a system. And now we can pop calc. And now we run into a sophisticated security mitigation that was added to Windows 10, where they don't allow you to spawn a calculator as a system anymore. And I don't know what this even means. And you can't click on the button, so it's weird. But an even more sophisticated attacker might then just pop something else. For example, Minesweeper. Right. So, and now this is probably also hard to see, but now this runs this system, and you can see that it's a subprocess of virtualBox.exe. Yeah, and the VM still works. All right, so I have a bit more time, so I can show you something else. When I looked at VirtualBox in the very beginning, I thought I found a really cool bug in VirtualBox, which actually wasn't. And it was actually a bug in Vagrant. This is a wrapper around VirtualBox. And what I noticed is that if you could create a symlink in a shared folder, you could then force that symlink to be opened on the host rather than on the guest. So you can then read and write every file on the host because you can just create a symlink to an absolute path. And it turns out the VBox, the VirtualBox shared folder file system implementation even had a flag where that would force that behavior. So if you're root in the guest, you can just do this and you can read and write files on the host. And you can even do the same thing if you don't have any privileges inside the guest because of this VBox user device. Because you can exploit all of this through HGCM. But it turns out this is not actually a VirtualBox bug because they usually do not allow you to create symlinks on shared folders. And you explicitly have to set a flag to enable this, which Vagrant does by default, and which you couldn't disable until recently. So if you're running Vagrant, then we would also always be vulnerable against this. And their solution is to just warn you now that you probably don't want this, and you probably shouldn't run untrusted code in the guest. And if you don't want this behavior, then you should set this opt-in environment variable that would prevent symlinks from being creatable. So if you're using Vagrant, you should definitely set that environment variable. All right, so my conclusion is that VirtualBox is quite a nice code base actually. It's if you're used to the directory structure, it's kind of easy to find where stuff is implemented. It's pretty structured in that way. And Oracle Security Response, in my experience, was pretty good. So they have this schedule where they only release security patches every 3 months. But usually, all the bugs that I reported to them, they fixed in the next upcoming release. Yeah, obviously, VMware is not the only one who has cool bugs and can be exploited. So I think it's really cool that they now added VirtualBox to Pwn to Own. Maybe we'll see more VM escapes there in the future. Yeah, and aside from this VM escape privilege boundary, there's other interesting things to explore, like the process hardening. And that's maybe a bit easier to get into. There's several issues there still, for sure. Yeah, and if you want to have a secure VirtualBox installation, I would advise you to not even try on a multi-user system, because probably there's tons of bugs still there that allow you to privilege escalate. You should disable all the features you don't need, especially 3D acceleration and video acceleration. And I think VirtualBox does a good job at making the defaults kind of safe here. So if you don't use drag and drop, it won't be enabled. So you have to actually enable it if you want to. Same for clipboard sharing and shared folders. So it's a bit different to VMware in that regard, where everything is just on by default. Yeah, some of these bugs, or most of these bugs, are only exploitable from kernel mode. So it helps to have a secure guest OS and do privilege separation inside the guest itself. And if you're using Vagrant, set this environment variable. All right, that's it from me. And if you have any questions, that would be a good time to ask.
Is there any questions?
All right, so if you think of anything later, you can probably find me somewhere and ask me in person as well.
Okay.
So thank you.
Thank you.